Okay, so you've got offshore pipeline construction, welding of duplex stainless steels. Is that right? Yeah, so that's what I've been told. Okay. So with all CRA materials, corrosion resistant alloys, welding is a lot more difficult than welding the API grades. And one thing that with duplex stainless steels you need to be very careful is contamination by carbon steel. Why is this? If the duplex stainless steel comes into contact with anything that's carbon steel, any of the API grades, a galvanic cell will form, and the anti-corrosion properties of the duplex stainless steel will be lost. So how can you avoid that? Well, first of all, do not use any tools that are made from carbon steel, or if they are made from carbon steel, they must be faced somehow with stainless steel. And also something that is very common, the use of grinding discs. Make sure that grinding disc hasn't been used before with carbon steel. That's one measure that it's very important. Another one is, in order to prevent the oxidation, particularly the root bit for duplex stainless steel, the root bit is extremely important, the first weld that you perform. And in order to prevent oxidation, it's very common to purge the pipe with in order to reduce the partial pressure of oxygen. And generally, there is a limit around 0.5% oxygen in the bore of the pipe. It's practically impossible to remove the quantity of oxygen, and it's actually there are no benefits, because in air we have a mixture of oxygen and nitrogen as well. And now remember what we said about stainless steels. How do we characterize their resistance to corrosion, particularly to pitting? We have that number that we called PREN, P-R-E-N, which was, what was it? Pitting resistance equivalent number. And that, if you remember, I don't remember the equation, but nitrogen is one of the elements that increases the corrosion resistance. So by purging the root, we also decrease the partial pressure of nitrogen. So if that happens, the PREN, the pitting number of the root will be decreased. Another important aspect is to control the heat input and the interpass. Now we've said that the root bit is very important. So generally you want to have the root bit thicker than the next pass. And that is achievable by using a high heat input. So high heat input means slower welding. Slower welding means thicker pass. And regarding the interpass temperature, so let's say we have a sound root bead. The next step is the temperature difference, the interpass temperature must be, and that depends on obviously the thickness of the wall, between 100 and 150 degrees Celsius. And generally, the heat input for the second pass must be lower than the heat input for the root bead. What else do we need to say here? Oh, what kind of consumables do we have to use? Well, generally the consumable must be at least, so what are duplex and it's 50, 50, 50, 50, austenite, 50 ferrite in this project. Now, generally, it is preferred, particularly for the root bead, to use a consumable with that percentage moving to 40, 60, actually having more ferrite in the consumable. And also, for an example, you may wish to perform the root bead with a consumable for duplex stainless steels to use super duplex stainless steel. So, for instance, to move from one with 22% chromium, use a consumable which has 25% chromium. So somehow the consumable use a more expensive consumable. So I think that's it about the most important aspects about performing welding with duplex stainless steels. Why it's important to keep the interpass temperature within these limits. So, in terms of the mechanical properties of the pipeline materials, we said that for the API grades during welding, one thing that you need to avoid is high cooling rates, because high cooling rates they suppress diffusion, and we end up with those phases that are hard and brittle in the heat effective zone. Now with duplex stainless steels, it's a little bit almost the opposite. You don't want very slow cooling rates. Can you guess what is that? What happens in stainless steels if they cool down very slowly? Remember that in our introduction we had a graph with the time required for some harmful carbides to precipitate in stainless steels. Remember that? If the cooling from high temperatures to low temperature takes a very long time, then we have a very long time for which is ideal for these carbides to precipitate. That's why we need to keep the interpass temperature within these limits in order to make sure that we don't have a very slow cooling rate to avoid the carbide precipitation. Because remember what's the effect of carbide precipitation? It will lead to depletion of chromium, and consequently the corrosion properties will suffer. Welding the cladded pipelines. So what is this clad? Well, generally all the CRA, the corrosion resistant alloys, based on nickel mostly, they are very expensive. So the clad applies on the inner side of the pipe usually, because we need to prevent corrosion. The corrosion is produced by the the hydrocarbons that are transported through the pipe. And generally, you see that's here the clad. So the thickness of the clad is much, much smaller than the wall thickness of the pipe here. And generally, that is only about 3 up to 5 millimeters. So you don't need a very high thickness clad material. But the problem is, how do we weld them? So we have the clad materials in this case made from an Inconel alloy, in this case too, but these welds that are on the side, they were made using 2 different techniques. With one of them, the second one, not so popular. Because we're looking at two things. One is that we want to produce a sound weld, and the other one, we don't want to increase the cost dramatically. So in the first case, the weld was made using a consumable made from the same material as the clad, so from Inconel, remember, which is very expensive. And in the second case, well, you can actually say from here that it's very obvious that we've used different materials for the consumable. So that's the root bit. What consumable do you think we've used here? Inconel, yeah, because you see it's exactly like here. But then the cap pass, that looks like the API. So you put the clad on any of the API plates. So this is an API plate. But you also notice there is something in the middle, which is neither that nor this. So the second method is to use a consumable made from the clad material, like here, just for the root bit. Finish the weld with an electrode made from carbon steel, but in the middle we put a buffer which generally is made from pure iron. Now, why do we need this buffer? And also there are some dangers in using just one material for the consumable. Well, we have 2 very dissimilar materials here. It's the Inconel and the steel. So, because of the high temperatures, there will be diffusion at the interface between them. So the properties of the Inconel, because that's why we put the Inconel there, we want to provide corrosion resistance, but because of the dilution of the carbon steel, the chemical composition will change. So in order to avoid that, so the idea is we use this the expensive electrode only for the root bead, and then we can use carbon steel, but we need to put this iron buffer in the middle exactly for that reason, not to have direct contact between the carbon steel and the Inconel. While this might be cheaper because you don't need to make the entire weld using an Inconel electrode, obviously it's going to take more time because you need to use basically 3 electrodes. So while it has been tried, it's not very popular. So commonly it's the just one electrode that is generally used. Okay. So next, I think you've discussed about the S-lay and how the welding is done there. You have a number of stations on the board, which is very convenient. Now, in J-lay, and why J-lay? because the SLA method can be applied. There are some limitations function of the depth of the water. So generally, for any depths higher than 1 kilometer, the SLA cannot be applied actually. So then JLA, as the name suggests, because the shape of the pipe follows the profile of a J. Considering this profile, how does the pipe sit on the barge? Vertical. Which means what? Can you have more welding or working stations? So no, generally you have just one. So because the pipe is vertical, there is a great interest in finding welding methods that we call a one-shot process. For instance, electron beam, laser, or friction welding. We'll have a brief look at these methods, but none of them was really very successful. So, despite of all trials, GMO, gas metal arc, do you mind if I call them GMO, because it's quicker? Gas metal arc welding. It's still the most popular one and the mechanized one. Right. So having just one station, it means that we must perform everything at this station. So that is the actual welding, the inspection, the coating, and so on. And here is a photograph showing such a station where, remember, welding, inspection, and applying graphic coatings take place. But how can we increase the speed of making the parts? Well, one way is to perform welding of a number of pipe lengths, and that can be 2, 3, 4, I think even 6 pipe lengths on the horizontal position, and then lift the top into what is called a tower. Because actually there are not so many vessels specially constructed for JLA. So it's very common to have a common vessel which is equipped with this tilting tower which will lift on the pipe, and then it allows to be laid down into the sea. Right. In terms of prototype welding and the electron beam, what you see here is an experiment, a test carried out by a company called Total. And as you can see, there is no sea around here because they performed the test on land. And the setup was in such a way that they had a bed which was with the ability to rock in order to simulate sea conditions, waves, and whatever. So they were rather successful with electron beam welding. But what are the inconveniences? So now the heat required for the welding is produced by an electron beam. For an electron beam to be efficient, you certainly need vacuum. So in order for the weld to be able to carry out the weld, you need somehow to create vacuum around the weld. So because it's more difficult to enclose everything in vacuum, what they did in this prototype test, they applied for the gun that produces the electron beam, you need generally very good vacuum. So they use a chamber with high vacuum for the electron gun, and a chamber with lower vacuum for the pipe. What we have next, the aspect of the weld on using just one shot, so a single pass, in a 28 millimeter wall pipe. It looks very good, it's a sound well, but actually applying this in the field, it's more complicated. Other type of trials were using radial friction welding. Well, in radial friction welding, the pipe ends which are clamped by a ring, which also a consumable ring, because the weld is produced by rotating this ring, and also you see the P here, it means that you apply a load in order to produce the friction welding. So it rotates with high speed, and that will some melting will be produced, but the metal from the ring will mix with the metal at the ends of the pipe, and in that way a joint is produced. And something else, well, obviously in order to avoid in order to avoid a deformation in the pipe inside the bore, we need to put a plug, an expanding plug. So neither one of these methods were very efficient, and particularly with radial friction welding, there is a risk of not having a sound weld. And the most common defects are loft. Remember what loft are? Lack of fusion, and you can see that there we have a lack of fusion in the weld. So to conclude all these methods, the laser, we'll see that laser, I think on the next slide, laser in combination with arc welding has been tried, and it's actually quite good alternative. But electron beam and radial friction, in spite of some trials which were successful to some extent, they don't find wide use in the field. But in order to speed up the construction and the welding, combining laser welding with GMO gas metal proved to be a good alternative. Why? Because in this case we get the advantages of each of the method. So the main advantage from the laser welding, deep penetration. The main advantage of the arc welding, very good feed up, because that's one concern with laser welding when applied alone. Okay. So we'll discuss next about the real barge, and we have an example here with a huge spool. This is a view from the top. A very clever way of actually transporting the pipe on site. And it's not a new technique. It was used for the first time in 1944, immediately after the invasion, the Allied invasion in Normandy. Sorry, I'm not very good at history. I think it was 44 or 45. That project, so the Allied, they needed somehow to carry fuel from Britain to the continental Europe, to France. And a very ingenious method was this project called Pluto. Pluto, and it stands for pipelines under the ocean. Pipelines under the ocean. And they did exactly something like that, similar to what you see here. The actual pipe is spooled onto a very big reel, which is positioned on the vessel, either like in this position with, horizontally, or with the axe parallel to the platform. And that allows for very long pipelines to be transported onto the site. One problem with this is obviously in order to roll this pipe onto the school, you need a huge area on land where this is done. The other limitation is because there are two techniques. You take the vessel close to the shore, and from the shore it is pulled directly onto the vessel, or the entire reel is taken out by a very large crane. It's deposited on the land, and after spooling, the crane will take it back onto the vessel. So the limitation is the power of that crane. Will it be able to actually lift it and put it on the vessel? Let's think, what other inconvenience? Well, from the materials point of view, what do you think? What happens with the pipe being bent here so much? What are the risks? Buckling. Yeah, sorry, I didn't understand. Yeah, ovality and buckling. And also,
what about the washer? Is present in this phenomenon?
Well, that's it. The strain induced into the pipe, the strain which can be, you can use a plastic measure up to 5%, which it reflects how in the mechanical properties. A loss in the yield strength, and also a loss in the ductility, so the pipe becomes more brittle. That's something that you don't want. Another thing is applying the way coatings. It's difficult because the way coat during this process will probably damage, so this is not actually applicable. Okay, and we have an example here of a reel sheet. Remember, in the previous scenario, the reel was with its main axis vertical onto the vessel, while here it is parallel with the surface of the vessel. What else do we need to say here? I think that's it. So this is how it's completely. Remember, you need huge areas on land in order to weld the pipes. Pipes which can be continuous, made by electrical resistance welding and high frequency induction, or the pipe pipes that are welded, and in this way you can construct a pipe that is a few miles length, and then they are spooled onto the vessel, like in this case. The vessel that we see here is an Apache. Okay, and then the pipe on the reel, we've talked about that already. Well, another option is to construct pretty much everything that is required for our pipeline, do it on land, and enclose everything into a pipe carrier. So you have a pipe that carries everything inside. Everything what? The main pipe with spaces for instrumentation, for heating, for electrical power. One advantage is that this can be also pressurized with nitrogen. Why is it good to have it pressurized? Because of the difference in pressure in the seawater. Having pressure inside, it means that the hydrostatic pressure from the sea will be basically eliminated, and also it provides resistance against oxidation or corrosion. And the bundles, the pipe bundles, they can be lowered into the sea very easily by flooding inside, so that the required buoyancy is achieved. Some examples here. I took this from your handout because a lot of projects use pipeline bundles. So one was Pan-Arctic in 1977, so it's not a new technique in the Canadian Arctic. Another one, 84-86, bundles up to 10 miles in Green Canyon. Another relevant project, this was carried out by BP, Green Canyon in Bullwinkle platform, 1996-97. Flowline bundles 14 miles long. And also in the North Sea, I'm going to give you just one example. If you want one example in the handout, Statoil in the North Sea, they made bundles. Doesn't say here how long, but the flow lines were made from 13% chromium stainless. So a lot of projects use pipeline bundles, and there is quite a large manufacturer here in Newcastle on the quayside. The company is called Wellstream. Have you heard of Wellstream? And they do manufacture of a lot of pipeline bundles. The major disadvantage is that, guess what? Let's say we've laid the pipe bundles into the sea. What's next, and what is the disadvantage can you notice? Carrying out repairs. Because if something goes wrong with any of the components inside the pipe carrier, then carrying out the repairs is going to be very difficult. And this is the way how the pipeline bundles are transported onto the site. So we need to use two tugs, a trailing tug and leading torque. And obviously, in order to maintain the required depth, and also to keep the bending of the pipe bundles within the limits, the speed of the two torques must be correlated with each other. Right. So for the next few minutes, we're going to start something that's very interesting. What options do we have to carry out welding underwater? Well, why is this necessary? Well, it's necessary for maintenance. It might be necessary for welding tie-ins, generally, because you can't do that on land and put them there. But a lot of these apply for carrying out repairs. And I will start with, let's say, wet welding. What does it mean? It means that you need a diver, so the welder is also a diver who dives into the sea, and there is no any kind of protection around it. The electrode is generally painted with something to protect it against the water, against the seawater. But that's pretty much all that it's done. Coffer dam usually if you need to carry out welding close to the surface. That is not very pleasant because close to the surface we are in the splash zone. In the splash zone where there are waves and we'll see immediately how a coffer dam looks like. It's basically a box in which the welder gets in there. It's fitted around the pipe, but there are no changes in the pressure, so the welding is carried out at the atmospheric pressure. And then a local dry chamber is very similar to wet welding, but we don't protect the welder. The welder still need to use diving equipment, but the actual welding equipment is encapsulated into something to provide protection. And the other, some special chambers. In one of them, the pressure is atmospheric pressure. That one. And as the name suggests, hyperbaric, because the pressure here is actually higher than the atmospheric pressure. So we'll have a quick look at all of them. This is the coffer dam. So remember, we are in the splash zone. This is the level of the sea. The welder gets into this box, which is fitted around the pipe. It carries out all the required weld. And basically the weld is carried out as dry weld as on land, because there is no water in there. The other case, the wet welding, exactly like that. So it's in direct contact with the water. So immediately you will think about the properties, mechanical properties in this weld. There is water. What is water? Well, it's seawater, so there are many things in there, but you have hydrogen, H2O. Hydrogen, because of the arc, hydrogen will be picked up into the weld, so expect to have a really bad weld. And generally, the mechanical properties of welds carried out in this way are around 80% lower than the welds carried out on land. Again, that region with very large graves, remember, where the austenite grows very large. that region, the size of the region is much larger in this case than for welding on land. So quite a lot of disadvantages. The advantage is that it's simple. You just need a very specialized welder, which is also a diver. Next, it's a little bit better. It's a local dry chamber. It's this. So actually, the welding equipment is encapsulated into some kind of box to offer protection against the seawater. So basically, the type of weld that is performing this way will be very similar to what you achieve on land. Hyperbaric. A few words regarding the wet welding, which was still is very popular in America, not so popular in Europe, and one reason probably it's the temperature of the sea being much colder in Europe, and the quality of the. But for whatever reasons, it hasn't become too popular in Europe. Hyperbaric chamber. Well, in hyperbaric chamber, some kind of box which simply needs to offer protection against the seawater, which is fitted onto the pipe where at the location where the weld is to be carried on. And you put the welder in, and you see this. That's a tube through which, in many cases, air is completely pumped. Because of that, somewhere at the bottom of this hyperbaric chamber, the pressure somewhere on this line. The pressure in the chamber equals the pressure in the sea. But as you go up, the pressure increases. So actually, the weld is carried on at pressures, which is also very important because remember that thermodynamic, very simple equation between pressure, volume, and temperature, PV equals nRT. But this is the most popular technique because it's so simple. So the welder gets into the box. He sends a signal to his mates on the vessel, start pumping, and they pump. He executes his job, and it's done. In some cases, the air can be replaced with a mixture of gases, particularly based on helium. Helium is a very low gas. And one reason for that is to help this guy because divers, they may suffer something which is called nitrogen narcosis. Narcosis. And narcosis, if you know what the term means, it's actually they after inhaling this mixture of gases, yeah, but the first symptoms are they feel like they're drunk, very drunk. So they basically cannot. At this stage, it's not dangerous. So as soon as they go a little bit up into the sea, so the pressure is lower, the symptoms will go away. But otherwise, they feel drowsy, and the symptoms described by divers is that they feel like drunk. So it's risky because they cannot carry out the work. Okay, just let me finish with what is the difference between hyperbaric chamber and 1 atmosphere chamber. Well, 1 atmosphere chamber, it means, so this is basically like a submarine, and it's completely closed, and the pressure inside is 1 atmosphere. Well, what are the advantages? The advantage is that in this way, the type of well that is performed, it's exactly, the conditions are exactly like conditions on land, so we know how to assess this type of well. But the technique is not, while, yeah, you might say it's probably the best, okay, but it's not very popular because it's expensive to achieve all of this setup. So, right, I'm going to finish with this one, yeah, the summary of the subsea well. So with the coffer dam, remember it's in the splash zone. It's expensive and limited worker depth, only in the splash zone. The wet welding, well, the poorest weld quality, it's achieved by that. It works well for repairs. Local dry chamber, it actually applies only to small areas because of the complex equipment. Hyperbaric, good quality, but remember the performance of the welder is affected by that. They get drunk. And 1 atmosphere, best quality, but very expensive. So actually, hyperbaric chamber, it's a lot more practical than 1 atmosphere. Okay, I think I'll stop here. Any questions? I hope I didn't miss anything important, so please ask if you have any.
Yeah. For the local dry chamber, can you control the cooling rate for the heat affected zone?
No, but we can control the cooling rate in any of the methods.
But I mean,
but the cooling rate, it should be higher because
of the water.
so you protect the electrode. You protect the electrode, and then it comes into contact with. So the arc is protected. There is no seawater affecting it. So it's dry. It's not wet. So the cooling rate with the portable device doesn't have any heating system involved, and it will probably depend on the temperature of the seawater actually. So if it's very cold, yeah, expect a high cooling rate. Okay. Any more questions? So I didn't give you enough examples about the projects involved with pipeline bundles, but you can find them in that handout about offshore pipeline construction.
I understand that here we're going to have Martinson and here we're going to have like 100% power.
Yeah.
But what happened here in the middle? This is not for the middle steel pipe steel, but here, let's say this curve.
Yeah.
Like.
Yeah. Well, you see, if you, let's take any of the curves here. So if we take, for instance, this one. Yeah. Okay, we take this one. Well, at this condition, so when the temperature is whatever value is there. Yeah, and if when cooling from this temperature to this temperature, it takes that long. You read the time from here. Austenite, here is austenite, yeah, we're at high temperature. Austenite starts to transform to ferrite, yeah. So during cooling from here to here, you have a mixture of austenite and ferrite. Then from this temperature to this temperature, you are in a region where it says that you have perlite. So in here, what do we have there? I think that's the benite section, yes, because this dotted line is upper benite and lower benite, or what's this?
I think this is the 50% perlite.
This is the 50% perlite, yeah? This is the 50% perlite.
That's also benite.
Okay, so the next stage, because remember we said that benite forms around 550 degrees Celsius.
Yeah.
So the conditions are for the benite to form here. So then you will have a mixture of ferrite, perlite, and benite. Yeah, and then it goes down, and this is the martensitic region. So ferrite, benite, perlite, and some martensite will also form here. So, okay, so this was 36. So can you check the composition of this?
Not really, because in the description they say they have different. It's not that detailed.
Right, okay. Yeah,
So
that's how it happens.
in all these corps, I'm gonna have martensite because they're crossing this region.
Yeah.
For all these corps.
Yeah. And you have only martensite here,
And also here, right?
and here, to all curves which do not touch this area. In this one, you will have a mixture of benite and martensite. Up to this curve.
And for this diagram, this region will be upper benite and this one will be lower benite, or just differentiate?
Well, that difference can be made, yeah, but do we have here a distinction between the benite?
I don't think we have.
No, so from this diagram you probably can't say which is lower and which is upper. Yeah?
Yeah. Well, I was just confused what happened here in the middle because we have like a mixture of different places.
Yeah. So austenite, ferrite, austenite, perlite, and then benite. So in the final structure, ferrite, perlite, benite, and some martensite.
And this line stands for what?
Oh, M50 means that you have 50% martensite. Yeah.
But why it doesn't like continuous?
This is because over there the martensite transformation stops. Because remember, it depends on the cooling cooling
So
time.
if the cooling is too slow to
If
get
it's too
martensite.
slow, it doesn't form anymore. Yeah.
Just like this kind of course.
Yeah.
Okay.
Yeah. So, for instance, on this curve, you have 50% of martensite formed, and that's it. You don't get more. Because if you want more, if you want to reach the 90% line, you need to cool this way, which is 2 seconds.
That's hardly possible.
It's possible to do cryogenic treatments.
Oh, okay, nitrogen.